So, what Dalton called an atom, it turns out, based on years of work, of experimental results done after Dalton's time, it turns out that what Dalton called an atom is actually made up of even smaller particles. It's not what he called the atom is not quite the smallest bit of matter that people envisioned at the time. So we now know, based on additional information, that they're actually made up of smaller particles, and these smaller particles are called protons, neutrons, and electrons. And so instead of a simple indivisible sphere just with no structure, so you could say that Dalton's model is a structureless sphere model. Okay, so Dalton envisioned an atom to be a structureless sphere. Okay, this Dalton's model is no longer accepted. Okay, we now know it's actually made up of even smaller particles called protons, neutrons, and electrons. And the way these protons, neutrons, and electrons are arranged in an atom gives us a name for this model of the atom. This is called the nuclear model. The idea here is that the protons and the neutrons are found in a very tiny spot, okay, called the nucleus. That's right in the middle of the atom, right? I have a picture right here with a nucleus right in the middle, okay? So that's where you find your protons and neutrons, and you can, since they're found in the nucleus, you can also refer to them as nucleons. They're in the nucleus. Now, the electrons, okay, in the nuclear model are said to be moving around the nucleus. So the electrons are right here, okay? And in the modern view of what an atom is, these electrons move really, really fast around the nucleus that it's really impossible for us to pinpoint exactly where it's at. So if you see those sketches of an atom where you have a nucleus and then you have electrons being drawn as dots around it, those are just for convenience, so you can count electrons. That's not really a valid picture of what an atom is. So if you want to imagine the electrons around the nucleus, imagine a very fast-moving thing around the nucleus. It's like it's just a blur. So it's convenient for us to visualize the nucleus moving around the nucleus as if it's a cloud. It's just a blur around the nucleus. Okay? Now, places between the electrons and the nucleus, there's nothing. So an atom is, in fact, mostly empty sphere. And like I said, Dalton's model is that of a structureless, indivisible sphere. This is no longer acceptable these days. We now know, based on additional information since Dalton's time, that an atom, as Dalton has called it, is in fact not structureless, it's not indivisible. It's made up of smaller particles, protons, neutrons, and electrons. And this is how they're laid out. Okay, so let's look at what a typical atom size, what the typical sizes are for the parts of an atom. The nucleus typically is around 10 to the negative 14. Remember we said that the distance between two atoms is around 10 to the negative 10 meters. Okay, so you can imagine that as the charge of the electron cloud, as the diameter of the electron cloud. So if I have this electron cloud right here, this diameter would be about 10 to the negative 10. Okay, that's one angstrom. And this diameter right here would be also 10 to the negative 10. So the distance, center to center distance, would be 10 to the negative 10 meters. Okay, so that's the typical size of the diameter of the electron cloud. The electron itself is even smaller than the nucleus. It's estimated to be less than 10 to the negative 18 meters. So let's take a look at these numbers. The electron cloud, how does 10 to the negative 10 compare to 10 to the negative 14? 10 to the negative 10 is much bigger than 10 to the negative 14, right? How much bigger? That's 10 to the fourth difference, right? 10 to the negative 10, 10 to the negative 14 times 10 to the fourth would give you 10 to the negative 10. So you have to multiply the nucleus diameter. This nucleus diameter you have here, you have to multiply it by 10 to the fourth. That's 10,000 times. So the atom itself, this distance right here, is 10,000 times bigger than this distance right here within the nucleus. So that's how empty the atom is. Because within that region where you have your electron cloud, the electrons are even tinier than the nucleus. There's just a few of them roaming around the nucleus. So an atom, we say, is mostly empty space. So although we refer to the size of the atom as the size of the electron cloud, most of that cloud is really empty. Okay? So how does the diameter of the nucleus compare to that of an atom? It's at least 10,000 times, 10 to the fourth. Okay? I'm sorry. Nucleus compared to the atom, it's smaller, right? So 10 to the 10,000 times smaller. It's much, much smaller than the atom itself. How would the volume of an atom compare to that of the nucleus? What's the formula for volume of a sphere? If we imagine the atom as a sphere. Volume of a sphere is 4/3 pi r cubed, right? So let's compare the volume of an atom to the volume of the nucleus. Well, it's 4/3 pi radius of the atom cubed divided by 4/3 pi radius of the nucleus cubed. Okay? So if we did this, 4/3 pi cancel out. That gives you radius of the atom over radius of the nucleus cubed. How's the radius of an atom related to the radius of the nucleus? How much bigger? Same thing as the ratio of the diameters, right? So the atom to nucleus ratio is 10 to the fourth, right? At least around that figure. Raised to the power 3. That is 10 to the 12th. So the volume, the space occupied by an atom, okay, the space occupied by your electron cloud is at least 10 to the 12th. So that's 1,000,000,000 times bigger than the space occupied by your nucleus. That's how small the atom is. That's how small the nucleus is compared to the electron cloud. Okay? The electron cloud is 1,000,000,000 times, 10 to the 12 is 1,000,000,000 times bigger than the atom, the nucleus. Alright, so let's look at this one. Imagine a stack of atoms that stretches from the ground to the top of the New World Trade Center, and that building is 1776 feet. So if you were to just imagine stacking just the nuclei, removing all the spaces between the neighboring nuclei, removing all the electron clouds, just stack the nuclei one on top of each other for a stack of atoms that goes from the bottom to the top of the World Trade Center. What would be the height of the building if we can squeeze out all the space between the nuclei? Go ahead and pause this. Oh, what did I do? Alright, so let's see how we can work this out. So imagine a stack of atoms, right? Each atom has a nucleus, right? And that goes up to 1776 feet, right? But now, imagine removing all the spaces between the nucleus, so we now just stack this circle here, this circle here, this circle here, and so on. Well, how much did we say this one compared to this one? No, diameters. 10,000 times, right? 10 to the fourth. So your length will be reduced by 10 to the fourth, right? So the new height, so your reduced height, you might say, would be the original height, 1776 feet, divided by 10 to the fourth. It's going to be 10,000 times smaller, right? Remember, this distance is 10,000 times smaller than this distance right here. So if you remove the gaps between the nuclei, just stack the nuclei right on top of each other, your distance is going to shrink to 10,000 times smaller. So what's 1776 feet divided by 10 to the fourth? Let's calculate that. Well, actually, you don't have to use a calculator for that, right? You just move your decimal point how many places to the left? 1, 2, 3, 4, so it's 0.776 feet. Okay, what's 0.1776 feet? Let's change that to inches. One foot is how many inches? 12 inches. Okay. So let's say do your unit conversions. 0.1776 times 12. This one I need a calculator. That's 2.13 inches. Okay? That's how much empty space there is in the World Trade Center. 1776 feet. If you can squeeze out all the space between the nuclei, that height shrinks to 2 inches, about the size of a needle or a push pin. Okay?